In this video, I would like to look at the XPS of a multi-layer material. In this example, we've got a polymer that has been deposited on a silicon wafer. It has been exposed to air, therefore we would expect adventitious material. But the polymer itself, if we can remove the adventitious material, ought to produce spectra that we see of this form. So it's a CHO polymer. We see a number of chemical states in both the carbon and the oxygen. And this is what we would normally focus on when we're doing XPS. But the silicon wafer does have an influence on XPS spectra, and I can illustrate that using a very simple test using principal component analysis. This is an experiment that will allow us to see what happens to XPS data measured from a multi-layer material. In this instance, we're sputtering with an ion gun that is a cluster source, 2 kV with 1,000 atoms per cluster, and when we sputter for 20 seconds and repeat the XPS measurements, we end up with carbon showing some change. This is the carbon chemistry CH. You can see it is diminishing relative to the double bond carbon oxygen type chemistry. There's some adjustments here, but they're really not very pronounced. And we see a similar change, but not particularly pronounced again in the oxygen 1s. But when we look at the survey measurements, while the oxygen and the carbon don't appear to have significant changes, what we do see is changes in the background. And we can try and understand what's happening to the background if we do a PCA on these survey measurements. Let's display 4 abstract factors. And in fact, only 2 of them are sufficient to make us aware of what is happening for this particular sample. So here's the average spectrum as calculated by PCA. It's not quite the average spectrum, but PCA works out the greatest variance in the data and presents that as the first abstract factor. And then the second abstract factor is the greatest variance once the first one has been removed from the data set. And within this second abstract factor, we now see what is happening. That while we did not see a significant change in the photoemission peaks, what was happening is a change in the background, and this change in the background is a consequence of having a sample that has a buried layer of silicon. So the photoemission from silicon is very small. The silicon 2s, silicon 2p, we do not see much in the way of signal in these data, but what we do see is the change in the background that is a consequence of these photoemission peaks emitted from silicon scattered throughout the silicon and the overlayer of the carbon polymer. And the result is a distribution of signal to lower kinetic energy that will alter the background to data. So when we're calculating backgrounds such as Shirley or Tugar or linear backgrounds, and we have a buried layer material, we may find some anomaly within the quantification that could be a result of alteration of the background due to the substrate of the silicon altering the background to the XPS.